Okay, in this video, I'm going to be looking at problems from section 3.3. All right, so in 3.3, that's where we were looking at product rule um, and the quotient rule. All right, so it suggests you look at 9, 11, 15, and 55. Let's go ahead and look at 9. Okay, so on question number 9, we're being asked to do the derivative of a function. All right, and right here there's an x, and here there's an x, and you have multiplication between those two functions. You cannot just do the derivative of each piece, remember. You have to use the product rule. And the product rule says you do the derivative of the first, which would be just e to the x, times the second function as is, plus the derivative of the second function, and that's a cosine, so the derivative of it would be negative sine x times the first function as is. Okay, and then you clean them up. So the plus and negative, I'll put a minus. I could factor out the e to the x, but that's not necessarily considered more simple. But on a multiple choice test, you need to be ready to identify your answer. I do think putting the e to the x first on that second term is helpful, so people don't think you're doing the sign that the parentheses are around x e to the x, because it's not the case. That's like after the fact. So I think this cleans it up a little bit for people to put the e to the x first, and then that's okay, or you could factor out the e to the x, but cosine x minus sine x doesn't wind up having an identity that you could use to make that any more simple. And that's all there is to it. All right, let's go ahead and take a look at question number 11, because it's a quotient rule. So on that one, we have a rational function, okay, and it can't be rewritten to avoid having to use the quotient rule. Well, it could be rewritten so that you could use the product rule, but it can't be rewritten to avoid both of those things. So the quotient rule just says take the derivative of the top, which in this case would be 1, times the bottom function as is, minus the derivative of the bottom function, which is also 1, times the top function as is, and then divide that by the denominator squared. Okay. Now these sometimes do get messy. This one's not too bad. If we just simplify that numerator, we wind up with a negative 5, because those x's cancel, over x minus 5 in parentheses squared. Okay. So section 3.3 was finding the derivative using the product or quotient rule. So we've done one of each of those. Let's go ahead. That's also just quotient rule. Let's go ahead and look at, all right, we'll do one more. How about 55? So that one is a product. See, there's an x in the beginning and an x at the end. So I'm going to do the derivative of the first times the second as is, plus the derivative of the second function times the first as is. You need to know all your basic derivative rules. So you need to know the derivative of tangent is secant squared, right? And then that would be 2x tan x. I'll put that x squared in front of the secant so you don't think it goes with the x. See, it's really this, and sometimes people misinterpret it. And there's not a whole lot you can do to clean that one up. Factoring out an x doesn't help that much. That would be a okay final answer. But like on a multiple choice test, they may not write it that way. They may write it this way, right? Which is also correct. So you have to get to where you can recognize equivalent correct answers. All right, and then another objective on the study guide was to do the second derivative. So let's do one that they recommend that's algebraic, and let's do one that's transcendental that they recommend. Okay, so if I look at question 99, the original function is 4x to the 3 halves power. So the first derivative would be 4 times 3 halves times x raised to the 3 halves minus 1. Okay. And you would probably have done that part in your head. So then that 4 times 3 halves turns out to be 6, and the 3 halves minus 1 turns out to be 1 half. And so we wind up, and on that one, you probably would see the answer written that way, but that's equivalent to this. Okay. So again, on a multiple choice test, you'd have to know which one's which. Oh, we're not done though. We got to do the second derivative. So I probably would not have changed it to a radical there and just do the second derivative. So that would be 1 half times 6 times x to the 1 half minus 1, which would give me a 3x to the negative 1 half. And you're not allowed to leave the negative exponents. Now remember when you rewrite this that the 3 is understood to be to the first power, so it does not move to the denominator. Only the second part, the x to the negative 1 half, is 1 over x to the positive 1 half. And that is probably the way I would recommend you leave the answer, since it started with a rational exponent, but it's equivalent to having 3 over the square root of x in the denominator. Okay. All right, let's look at 103. This one can be a real challenge for people because of the sine and cosine that you wind up with. So it's a product, and also it's a product rule here, x sine x. The other one was not. It just had a constant. So that's not a product rule problem. That's just bring down the 4. So if I did the first derivative, I'd have to do the derivative of, see, here's two functions that involve x. That's a product rule problem. So I do the derivative of the first times the second, plus the derivative of the second, which is just cosine x, times the first as is. But that x that I just wrote is not going to become x squared there. This cosine x is its own thing. So before I redo this or do the next one, let me just rewrite this with that x in front of the cosine, so there's no misunderstanding about that. All right, now I've got to do this a second time around. I'm going to move over a little bit. So I'm going to do the derivative of sine, which is cosine. And then, so because of the plus, I could just do the derivative of each piece, right? Then I'm going to come over here and do the derivative of the next part, which is a lot like what our original function looked like. So here I'm going to be doing the derivative of the first function, so the x times cosine x, then plus the x by itself, and then the derivative of cosine is negative sine x. Okay, and then this is cosine x, so there's 2 cosine x's. And then I have a minus, a negative, x sine x. Okay, and there you have it. All right, let's go ahead and do this one. 3, 4 is where we started with the chain rule type problems. So they recommend 13, 15, and 17. Let's go ahead and look at 17 because it involves the most work. So with 17, you have a radical, and underneath that radical is not just s. It's got a whole lot of other stuff on it. Okay, so what you'll want to do first is rewrite it so it looks like a power function. So it would be -2 and then the quantity 5s squared plus 3 raised to the 1/2 power. So now you're going to do the derivative. So you're going to bring the constant down, you're going to multiply, bring 1/2 in front, and then you're going to have that times the 5s squared plus 3, subtract 1 from your exponent, so you'll get a -1/2, and then this is why it's called the chain rule sometimes, because then you have to do the derivative of that inside function, and that would wind up being 10s, wouldn't it? Okay, then you clean it all up. So we have a negative here, we have a -1 times 10, that's -10s, and then the 5s squared plus 3 is to the -1/2 power, so that'll move to the denominator, and it's a square root, so I'll go ahead and put that back in, and there you have it. Okay. Right. I don't know why I put those in there, those two. Let me see if I'm missing something. Okay. No, that's okay. All right, so let's go ahead and take a look at the chain rule when you have a trig function. All right, so maybe 37 might be a good one to look at for that, because that was really hard the first time we did this to really get a sense of what's what. What I'll probably do two of these. Let's do 33 first. All right, so on 33, we're trying to do the derivative of y equals cosine of 4x. That 4x is the input to the cosine function. So you'd multiply by 4 first, then take the cosine. So when you use the chain rule, you take the derivative of the outside function. Derivative of cosine would be negative sine, and it would be of 4x still. But then you multiply by the derivative of the inside function, which is 4, and then you just clean it up. Negative 4 sine of 4x. Okay? All right, let's take a look at 37. On that one, we have pi x in parentheses squared, and we're doing the sine of that. This really means that you multiply by pi, you square, and then you do sine. Okay? So the outside function is sine. So when I do my derivative, I'm going to start with sine and think, okay, the derivative of sine is cosine. I need to do cosine of the pi x, and the pi x is in parentheses squared. So it really means this. Okay, so that's the derivative of the outside function. Then I'm going to multiply that. I'm going to work on now the derivative of this. So see how it's something squared? So I'm going to start by bringing the 2 down, multiplying that by pi x to the first power, and then I need to do the derivative of the inside, which is just pi. Okay, and then try to get it looking good. So let's see, I'm going to put, okay, so this right here is 2 times pi times x times pi, right? So that's going to be 2 pi squared, 2 pi squared x, and then I have the cosine of pi x squared. I'm putting the extra parentheses just to emphasize that the cosine wasn't getting squared, just pi x was getting squared. So that would be the result on that one. Okay. All right, let's see. I think that's fine. We've done enough of those. Okay. Right here, derivative of an exponential function that involves the chain rule. Let's try 59. So on that one, we're starting with y equals e raised to the square root of x power, which means that's e with x to the 1/2 power. So x gets raised to the 1/2 first, and then you do e to that. So when you go to do the derivative, you start with the e, the outside function. So you take the derivative of e, which is e raised to the x to the 1/2 power, but then you have to take the derivative of x to the 1/2. So wouldn't that be 1/2 x to the negative 1/2? Okay, and then try to write it neatly. So I see the e to the square root of x. Okay, I see this negative on that x, so that's going to move down here and just be a square root of x. And then that 1/2 I could write as, the 1 is kind of there with the 2 on the bottom. So, So e to the square root of x over 2 square root of x would be a good way to leave that one. Right, and then what about if you had a log function? So let's look at 73. On that one, if I'm trying to do the derivative of it, I think about how I have x getting squared and then 3 is added to it. And after that happens, I do the natural log. So when I do the derivative, I start by the derivative of the outside function, so natural log. That's going to be 1 over x squared plus 3. But then I need to do the derivative of the inside function, which would be 2x. And then that 2x is like on top there. And you can't knock the x's out or anything because x is not a factor of the denominator. There's a plus sign there. So that would be a good way to leave that answer. All right, let's look at one more log one. Let's do 79 or 81. Let's go ahead and just do 79. Okay, so on that one, on this one, the original function is a log of something, and you have a product in there and some other stuff going on. So rather than trying to do 1 over all of that and then having to do the derivative of this inside, which would involve the product rule, you can use those log properties to separate this into the natural log of x plus the natural log of the square root of x squared minus 1. So that's very helpful. Like here, I could change it into natural log of x. This would equal natural log of x minus the natural log of x squared plus 1. So that's very helpful. Now, you can't separate out these pluses, like here, x squared plus 3. That's not the natural log of x squared plus the natural log of 3. That's not what the log properties say. It says if you have a product, you can rewrite it as the sum of these two logs, okay? And if you have a quotient, you can rewrite it as a difference of the two logarithms. So I'm going to continue expanding just a little bit more. I'm remembering how this right here is really x squared minus 1 to the 1/2 power. So I'm going to expand this a little bit more, okay? Let me go ahead and write that first. So that's really to the 1/2 power, okay? So I haven't even done a derivative yet. A log property tells me that this is true, that I can bring the exponent down in front. So after having done all of that, then I could start, I'm going to go ahead and erase this, go ahead and do the derivative. So y prime would equal 1 over x plus, bring down the constant, 1 over x squared minus 1. But this one, I would need to do the derivative of the inside, which would be 2x. Over here, the derivative of the inside would have just been 1. So one form of the answer might be just 1 over x plus, and then here, when I clean this up, this 1/2 and this 2 would become 1, and I would just have x over x squared minus 1. And that might be the answer on the multiple choice test, or they might have gotten common denominators. So you have to be careful about that. So like they might have taken and gotten a common denominator, like x, multiply it by x squared minus 1 and do the same on top. And then over here, you have the x squared minus 1, so multiply by x on the top and bottom, okay? And this would be x squared minus 1 plus x squared over x times x squared minus 1. So that's one of my worries about the multiple choice nature of the test, is recognizing like this might be the way you do it, and that might be the way they do the answer on the test, but this is another form of the correct answer. So just be aware of that, and maybe if your answer doesn't look like one of the answer choices, but you're confident you're right, try to look to see if you can figure out an equivalent correct answer. All right, I'm going to stop at this point.